In this video, we will learn about heap data structure. Data structure and algorithm goes hand in hand. Ultimately, you will be converting some kind of logic into a code. Now this code should solve some kind of problem. So heap data structure is very important to understand something called as priority queue. Priority queue is highly used in various competitive questions. Also it is heavily asked in interviews as well. There are two different types of heap: max heap and min heap. If you understand any one of them, well, it's very easy to understand the other. In this video we will learn about max heap. But once you understand the entire heap structure, you will realize that there is nothing much to learn about min heap. Okay, so let's get started. So what is heap? Well, heap is a data structure that has two properties. First, it is a complete binary tree, and second, the value of root must be largest among all its descendant nodes. So first, let's try to understand what second property is. So let's say you have a tree, something like this. So what second property is saying? That value of any node must be largest among all its descendant nodes. That means the value of this particular node will be largest compared to all its descendant nodes. And this is true for every single node. Look at this particular node, right? So the value of this particular node will be greater than the value of all its descendant. So that's what the second condition is. But what is the first condition? What is this complete binary tree? Binary tree means a tree where every single node at most two children, right? So this you can say is a binary tree, but this you cannot say a binary tree because this parent node has three different children. Okay, so a complete binary tree is obviously a binary tree. That is the first condition. Second condition is that all the levels should be filled except possibly the lowest one. So this is the second condition, that all the levels should be filled except for the possibly lowest one. So what does it mean by filled? Well, let's say you have a node. Now as it is a binary tree, you can have at most two children to this particular node. But let's say you only have one, and that is a right child. So what about the left one? Well, there is no left child. So we can say this level is incomplete. But let's say now you also have the left child. So we can say this level is complete if only a right child is present. We say level is unfilled or level is incomplete. Third condition is last level should be filled from left to right. If any tree satisfies these three conditions, we say that tree is a complete binary tree. Let's look at the very first example on the left side. So the very first condition is it should be a binary tree. Is it a binary tree? Yes, it is. Why? Because every single node has at most two children. Let's look at the next condition. Every single level should be completely filled except for the last one. Okay, is this level completely filled? Yes. Is this level completely filled? Yes. Is this level completely filled? You have the element here, but you don't have the element here. But this is the lowest level, right? So if lowest level is not filled, there is no problem. So the lowest level should be filled from left to right. You have an element here, you don't have the element here. So the lowest level is getting filled from left to right. So the very first example, we can say that it is a complete binary tree. Let's look at the second example. Let's start. Is it a binary tree? Yes, it is a binary tree. Why? Because every single node has at most two children. Look at the second condition. All the levels must be filled except for the last one. Well, is this level filled? Yes. Is this level filled? Yes. You have left child and you have right child. So that level is also filled. Let's look at the last level. Well, it is not filled, right? You should be having a left child here. So it's not filled. And you should be having right child here. So this level is definitely not filled. But our second condition tells us that all the levels should be filled except for the last one. Okay, so first condition is good, second condition is also good. Let's look at the third condition. The lowest level must be filled from left to right. If you observe carefully, there is no element to the left of 5, right? That means the lowest level is not getting filled from left to right. That means this particular tree is not a complete binary tree. Look at the final example. Is it a binary tree? Yes, it is a binary tree. Are all the levels completely filled? This level is filled. This level is not filled. Why? Because there is no left child to it. So the second condition is invalid. So the third tree is not a complete binary tree. What is heap data structure again? It should be a completely binary tree and the value of root must be largest among all its descendants. Let's try to understand how exactly are we going to represent this particular heap data structure. See, if you see something like this, you understand what it is. But a machine or a computer is not going to understand what this is. You need to store this data in some kind of format, some kind of data structure that is pre-built. So in this case, we are going to use dynamic array or vector. You can understand by just looking at the array, right? So see, how we are going to store. The very first value will go to the position 0. The left child of this particular element will go to 2 into I plus 1 position, and the right child will go to 2 into I plus 2 position. 7 will be stored at index 0. Now if you apply the formula 2 into I plus 1, that means 5 should go to index 1 and 4 should go to index 2. Again, so where 2 is going to go? Index of 5 is 1, correct? So 2 into I plus 1, that is 2 into 1 plus 1. The value of this is going to be 3. So 2 will go to third index and 3 will go to the very next position. 2 into 1 plus 2, which is going to be 4, and this is the position for 3. Now where will 15 go? The index for 4 is 2 and 15 is the left child. So left child will go to 2 into I plus 1. That means 2 into 2 plus 1. This value is 5. So 15 will go to the fifth position. Any data structure will be a heap if it is a complete binary tree and value of any node is greater than all its descendant. So 7 is not greater than 15. That's why this is not a heap, but it is a complete binary tree. So we just saw how exactly we are going to represent the complete binary tree. So very first element will go to the index 0. Left child will go to 2 into I plus 1 and right child will go to 2 into I plus 2. That's what we have written here. If a node is stored at ith index, then the left child will go to 2 into I plus 1 and the right child will go to 2 into I plus 2. Once you understand the representation, we can definitely determine the position of the parent node as well. Imagine your left child is present at index L and parent is present at index P. So L is going to 2P plus 1, correct? P is the index for the parent and L is the index for left child. Okay, so what will be the value of P? L minus 1 divided by 2 is going to be the value of P. Once you know the index for any element, let's assume that is I, you can definitely know the index for the parent. Index for the parent is going to be I minus 1 divided by 2. So you know the left child index, you know the right child index, and you also know how to find a parent index if a node is stored at ith index. Now we will look at 3 different operations. The very first operation that we are going to look at it is an insert operation. Imagine you already have a heap. Now what they are asking you to insert a new element into this heap. So the process to insert a new element is very simple. So you always add that element into the end of the heap. Now adding that value to the end of the heap will still maintain binary nature and it should be a complete binary tree. No problem there. But the value of that particular node might not be smaller than all its parents. So what you need to do? You need to compare the new element with the parent, and if parent is smaller, you swap them. Let's look at the first example. This is the heap data structure that we already have. They are asking us to insert 15. So we added 15 to the end of the heap. Correct? But now adding this 15 has broken the second rule of the heap, which was the value of any node should be larger than all its descendant. Now the value of 7 was higher than 5, 4, 2 and 3. Earlier it was okay, but after adding this element 15, now our second condition has been broken. So we need to fix it. So what we do? We will compare this 15 to its parent, and how we compute the parent? Remember, the parent is going to be I minus 1 divided by 2. So first we check 15 and 4. Now 4 is less than 15, so we swap. Now we have 15 here and we have 4 here. Now we again check 15 and 7. Well, the value of 7 is smaller than 15. So we swap again. And that's how we manage to correct the heap. Let's look at the code now. Very simple code. They are asking you to insert the value v into our heap. Remember, we represent the heap data structure in the form of dynamic array or vector. So we are going to add that value into our existing data structure. And that value will be added at the end. We take the index of that particular newly added element. We check whether the value of parent is less than the value of current node. If that is the case, we simply swap and we update the index value. Remember, this index will be representing the index of the newly added element. Let's try to run this code on given example. So we added 15 to the end of the array, right? So the index for 15 is going to be 5. So we check with the parent. The parent index is going to be 5 minus 1 by 2, which is 2. On the second index we have 4. See, this is 0, this is 1, this is 2. On second index we have 4. We check whether 4 is greater than 15 or not. Well, it's not. 4 is less than 15. So simply what we do, we swap. So 15 will be removed from here. You will have 4 and 15 will be added here. Also we will update the value of index. Index was 5 initially. Now the value of index will become 2. Again, let's check with the parent. Let's compute the index for the parent, which will be I minus 1 by 2. Here it should be 0. Now on the 0th position we have 7. Compare the value of 7 with 15. 15 is larger than 7, so we are going to swap it again. So here we will have 7, here we will have 15. We again update the value of index. Now index will become 0. Here I have explained the insert operation. Look at this. We have added 15 to the end of the array, correct? Now 15 has an index 5. We check with the parent. The parent index will be 2 and we know that 4 is less than 15. So we swap it. Look at this. And after the swap, our heap will look something like this. The index for 15 has become 2 now. We will check with its parent, which will have the index 0. 7 is less than 15, so we will swap it again. After the swap, this is how our array will look like. 15 and 7 will be swapped. And this is the heap. This is complete binary tree. Also, for every single node, the value of that node is greater than all its descendant. So 15 is greater than all its descendant, 7 is greater than all its descendant. Second operation that we are going to see is a delete operation. We are going to take that particular node which they are asking us to delete and we will swap that node with the very last node. Now, we haven't deleted anything. We just swap the given node with the last node. Always the last node. Now we need to remove that last node and that's what we will do. But the very first operation that we perform, that is a swap with the very last element, it might end up breaking our heap properties. That's why we need to perform something called as Heapify Operation. Now what is Heapify Operation? Well, Heapify Operation takes the node and put that node into its correct position so that the tree will become heap. Let's try to understand by taking an example. Let's say they are asking us to delete the element 15. So as per the first step, we will swap 15 and 4. So it will look something like this. Here we will have 4 and here we will have 15. Still we did not remove the 15, right? So we are just going to remove that element and we will have an array with no 15. Now this is no longer a heap. The value of this node should have been greater than value of all its descendant, but it's not. 7, 5 are greater than 4. So we need to perform an operation called as Heapify, which takes the index of a node and put that node in proper place so that ultimately we will have a heap. So something like this will happen. 7 will go up, 4 will come down and you will have heap. So Heapify operation is not something magical. Well, it's very simple. It computes the largest value, comparing the current node, left node and right node. In this case, 7 is the largest one. So it will swap that particular value with our current node. And that's what Heapify does. Let's look at the delete code. So first we find the index of a value that they want us to delete. Once we have the index, we swap that particular index with the very last element. We remove the last element and we heapify. Right? That's what we have done. We found out the index of 15 was 0. We swapped that value with very last element. We removed the very last element. Once we got this array, we realized that our swap operation has actually destroyed our heap. To fix that heap, we perform something called as Heapify. Well, Heapify is a recursive operation that places a node in its correct position in a heap so that the subtree rooted at that particular node will satisfy the heap properties. We first compute the largest value. So who is largest, right child, left child, or the current node? If the current node is the largest one, then we already have a heap. So we break, we do nothing. But if left child is larger compared to the current node, then simply we are going to swap our left child with the current value. So this swap might end up breaking our heap properties. So we need to heapify the left child as well. Same thing goes for the right child. If the largest value is the right child, we simply swap the current node with the right node. Now that swap might end up breaking our heap. So we need to heapify our right child as well. Let's try to understand this by an example. Let's say they want us to heapify this particular 7. So what you will do, you will check who is largest among 3 different elements: current, left child, right child. Right child is the largest. So what we do, we swap. So here you will have 15. After that here you will have 7. Now this swap might have ended up breaking the heap. So we need to check again. So we heapify this particular node. So what we do, we compute the largest value from the current node, left child and right child. In this case, the largest value is the current node itself. So we don't have to do anything and we have managed to rebuild our heap. Let's look at the code. So this is initialization portion. Here we initialize 3 different variables. One is largest. We assume that our current node, that is index I, is the largest. This is the left child. This is the right child. We check whether our left child is greater than our current node. If that's the case, then we update the largest index. We do the same with right child. Now, if largest node is not equal to the current node, then we swap our current node with the largest node and we heapify the largest index. That largest index could be the left or right one. Let's say they are asking us to heapify node 4. So how will it look like? Well, the very first thing that we are going to do is we are going to find the largest among the 3. The current node, the left node and right node. Who is the largest? Well, it's the 15. So what do? You swap 15 with 4. So now you have 15 here and now you have 4 here. But after the swap, we need to heapify this element again. Why? This 4 might not be the largest among its descendants. So we need to heapify this 4 again. So what we do? So we compute the largest among the current node, the left and the right. Well, there is nothing to the right. So we can say this is a very small number. Here in this case, it is the left node. So we swap. Now we will have 7 here and we will have 4 here. Again, we will heapify this element. But there is nothing on the left, there is nothing on the right. So the largest value is going to be the current value, which is 4, and we will break the loop. So after performing Heapify operation on the 4th element, that is index I is equal to 0, we get this particular tree. Now let's do Heapify on node 2. So what we do? We compute the largest among the current node, left node and right node. Well, the left node is largest among the 3. So we swap 5 with 2. Now we will Heapify the node 2 again. There is nothing on the left and there is nothing on the right. So the largest is going to be the current node. Once the largest is current node, that means we are going to break the loop. So after performing Heapify on node 2, we will get this kind of structure. Now this Heapify, as we have mentioned previously, is used to place the node in its right position. So if I perform Heapify on every single node, ultimately we will get a heap. See, this is the random array that we have here as an input. We need to rearrange the elements of this array so that it will form a heap. So if we perform Heapify operation on every single node, ultimately we are going to get a heap. But we don't have to perform Heapify operation on every single node. Why? Because performing Heapify operation on the leaf node, it's just the waste. Because there is nothing to the left or there is nothing to the right. So we are going to perform Heapify operation on the elements who actually has some kind of descendants. It's very easy to observe that you don't have to perform Heapify operation on n by 2 minus 1 elements because all those elements will not have any kind of children. Let's perform Heapify operation on the second index. Now on second index we have node 4. Once we perform the Heapify operation, we will get 15 here and 4 here. How? Well, we select the largest number among the three, the current node, the left node, and there is nothing to the right. So the largest is 15 and we swap it. We perform Heapify again on 4, but there are no children, so we are going to break the loop. Once you perform the Heapify on the index 2, we get this array. After that, we will perform Heapify on the very first index, that is node 2. Now node 2 has two different children, 5 and 3. Among all these three elements, the largest one is 5. So we swap 5 with 2. Again we will perform Heapify on node 2. There are no left or right children, so the current value is going to be the largest, and that's the breakpoint for us. So this is the array we will get after performing Heapify on the first index. Let's perform Heapify on node 7. So 7 has two different children, 5 and 15. Which is the largest? 15 is the largest. So we need to swap 15 with 7. And this is the array that we get. Again we will perform Heapify on 7. 7 has one children, that is 4. Now take the largest one. Here largest one is going to be 7. So if largest one is just the current node, we break the loop. After the complete Heapify operation, we get 15, 5, 7, 2, 3, 4. The array will look something like this. 15. Now look at this. This is completely binary tree. Also, the value of every single node is larger than all its descendants. 15 is larger than all of them. 5 is larger than 2 and 3. 7 is larger than 4. So ultimately you have a heap data structure. We take the input array. We apply Heapify on every single one of them except for the leaf node. And we start from right to left. Well, if you look at it, the time complexity of insert is very simple to prove. It is log n. How? So what we do in our insert operation, we append the node at the end of our heap. Then we check with the parent and we keep on swapping until we put this particular node, new node, to its correct position. The total number of operation is just equal to the height of this binary tree. Remember, this binary tree is a complete binary tree. The height of this is going to be log n. So you can have the number of operations in terms of log n. That's why the time complexity of the insert is going to be log n. So what will be the time complexity of Heapify operation? Let's look at the Heapify, then we will go back to the delete operation. Because we use this Heapify operation in delete, if you remember. So let's try to understand this Heapify operation and the time complexity of it. It's very simple to see. If you look at the code as well, let's go to the code. So we check who is larger among the current node, left and right. If current node is the largest, we break, and that is done. If left node or right node is larger compared to the current node, well, we swap and Heapify again. So let's say your I starts from 1. After that it will become 2. After that it will become 4. After that it will become 8. Yes, definitely 1 will be added also, but I am just assuming that it is getting multiplied by 2 always. So we keep on doing this until all the nodes are finished. So how many operations will require to reach nth node? Well, it's going to be log of n. We already seen this, right? Log of n base 2 means number of times you need to divide n by 2 till it reaches 1. So let's say it goes something like this till n. So the total number of steps is going to be number of times you need to divide n by 2 to reach 1, and that is log n base 2. Well, delete is also very simple. What we do in delete? We swap the very first element with the very last element. Once we do that particular swap, we remove the last element. Now our last element, which has changed its position because of the swap, will create problem for us, will destroy our heap properties. So you need to heapify that particular node. Again, heapify will take log n time. All the other operations are just going to take constant amount of time. That's why the delete operation will also have the log n time. Now to build the heap, what we did earlier, we started from n by 2 node in reverse order till we reach 0, and we heapify every single node. So you have n nodes and heapify takes log n time. So it looks like the time complexity of build heap is n log n, but surprisingly it is O of n. We are going to prove it. Very simple proof. We know that at every single height edge we will have at most n by 2 to the power h plus 1 nodes. You can verify this by using the above examples as well. No problem. Remember, this comes from heap being a complete binary tree. So at every single height h, you will definitely have at most n by 2 to the power h plus 1 nodes. Now at height h, it will take O of h time to perform the Heapify operation. Remember, Heapify operation checks for the current node, left node and right node values. And if values are not in proper order, it swaps and goes down into the descendant chain. So it will keep on going down till it traces the entire height h. So for every single node at height h, the Heapify operation is going to take O of h time. Yes, I know that we already said that Heapify operation is going to log n time, but that's the worst case. That's the entire height of the tree. But you will not be doing Heapify on the root every single time, right? You do Heapify operation on all the below nodes as well, and they are not going to take log n time. They are going to take time based on the height. At every single height h, you will have n by 2 to the power h plus 1 number of nodes, and every single node is going to take h time. The value of h varies from 0 to log n. This is the ultimate time complexity that we will have, and that's what we have written here. So you take this n by 2 outside of this summation, because n is not going to vary, 2 is not going to vary. The value that is going to vary in this summation is h. H by 2 to the power h, it's just a constant value, and it can take at max a constant value 2. It can never grow beyond 2. So you have n by 2 into a constant 2. So ultimately you will have the time complexity of O of n. So just for the sake of understanding, I will also provide the proof why h by 2 to the power h is not going to grow beyond 2. So we need to prove summation of h by 2 to the power h will be less than or equal to 2. Let's say h varies from 0 to infinity. Remember, in our given example, h varies from 0 to log n. But we are saying we will take the max value. So h varies from 0 to infinity. Surprisingly, the proof of this comes from the summation of GP. So let's say f of x is 1 plus x power 2 plus x power 3 dot dot infinity. This is summation of GP. Let's multiply both sides by x. So you will have x power 2, x power 3 till infinite. So this is, let's say, 1 and this is 2. So you subtract 2 from 1. So you will have 1 minus x into f of x is equal to, this x will cancel out this x square will cancel out this x square, this x power 3 will cancel out this x power 3, and all of them will be cancelled out, and you will have 1 here. So f of x is going to be 1 by 1 minus x. Now f of x is a GP summation. So it will be x power h, where h varies from 0 to infinity. The value of this is going to be 1 by 1 minus x. Let's differentiate on both the sides, and you will have x power h minus 1, h is going to be here, 1 by 1 minus x squared. Let's multiply by x on both the sides. You will have h varying from 0 to infinity, h x to the power h, and you will have x by 1 minus x to the power 2. So this is what we managed to prove from the summation of GP. You place the value 1 by 2 in this x, and you will get summation h is varying from 0 to infinity, h by 2 to the power h is equal to, remember we are replacing x by 1 by 2. So here it will be 1 by 2 and here it will be 1 by 2. Correct? So the value of this entire RHS is going to be just 2. And we managed to prove that summation of h starting from 0 to infinity h by 2 to the power h will have at max value 2. See, we have taken h till infinity, but we will only have h growing till log n. So definitely h by 2 to the power h will be less than or equal to 2. And this is what we used here.